If, for a given base, you create semicircular cross-sections sticking toward you and away from you, you have created circular cross-sections. Since the formula for the area of a circle is pi r squared, the formula for a volume with circular cross-sections is integral from a to b of pi r squared in terms of x or y depending on which axis you are perpendicular to. For our warm-up example, use the region bounded by x squared and negative x squared from 0 to 1 as shown in the graph at the right to create a volume by using circular cross-sections perpendicular to the x-axis. Perpendicular to the x-axis means in terms of x. The radius is x squared. The diameter is 2x squared. And for this problem, we're only going to set up the integral, and that would be our volume. Circular cross-sections can also be formed by revolving very thin, essentially no width, rectangles about an axis of revolution. These circular cross-sections are more commonly called disks. A volume formed by revolving a region about a line that does not pass through the interior of the region is called a solid of revolution. The line is called the axis of revolution. If a region is bounded by the axis of revolution, the volume of the solid of the revolution is the sum of the volumes of essentially an infinitely number of cylindrical disks. Our disk formula is integrating the area of a circle. I encourage you to check out this video I have linked in the description to get a better picture of what the volume looks like made by revolving disks. Set up an integral for the volume of the solid formed by revolving the region bounded by x squared. This is actually giving the same shape that we had in the warm-up example. Same volume. Y equals 0 is one of our boundaries, but it's also our axis of revolution. If one of your boundaries is your axis of revolution, then you will use the disk formula. From 0 to 1, and since we only needed to set up an integral, here is our answer. This time we're going to find the volume of the solid formed by revolving the region in quadrant 1, bounded by x squared, x equals 0, y equals 4, about the y-axis. Begin by graphing. Just like when we did volume with known cross-sections, your representative rectangle should be perpendicular to your axis of revolution. So our representative rectangle should look like this. Because they're asking us to revolve about the y-axis, that means that our axis of revolution is also one of our boundaries, so we will use the disk's formula. But this time in terms of y. Because we are revolving around the y-axis, our volume should be in terms of y, but we were given a function y in terms of x, so we're going to need to solve for x here. And we know it's actually the positive root y because we're only in the first quadrant. So for our limits of integration, we go from 0 to 4. Remember, it's least to greatest in terms of y. And then our radius of the revolving solid is root y, which should be squared. Integrate and simplify. The volume of this revolving solid is 8 pi. When a region is revolved about a line which is not one of its boundaries, its volume is formed from a sum of volumes of washers. At least some of the disks have holes in them. The washer formula is very similar to the disk formula where we have pi times the integral from a to b, but inside our integrand is the outer radius squared minus the inner radius squared. Set up integrals for the volumes of the solids formed by revolving the region bounded by y equals negative x squared plus x and y equals 0. We know this is disks because y equals 0 is one of our boundaries and it's our axis of revolution. Our boundaries are 0 and 1. The volume is equal to pi times the integral from 0 to 1 of r squared with respect to x, and r is negative x squared plus x. Remember that we use the disk formula when the region is bounded by the axis of revolution. We'll use the washer formula when the region is not totally bounded by the axis of revolution. And we'll cover the washer examples in the next video.